Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the lecture 13 of the course E207 Electronic Devices and Circuits. Today we'll talk more about bipolar junction transistors. In the previous lecture we studied the brief working functions of these BJTs, how do they work, their design, and today we'll go into the more detail. My name is Deepak Jain, I am an assistant professor at the Electrical Engineering Department of IIT Bombay. So, these are the contents of the today's lecture. So, we will first briefly talk about input and output characteristics of the common base transistor. We were discussing common base configuration in the previous lecture, so we will take that forward. So, we will see how this current versus voltage is there in case of input junction and how it is in the output junction, which is a reverse bias junction basically. The input one is the forward bias. So, if this is, let us say P and P. So, this is forward biased and this one is reverse biased. So, IV characteristics of this junction, input, and IV characteristics of this junction are the output ones that we are going to look into that. Then we will talk about the static characteristics of the bipolar junction transistor, especially in terms of the charge carriers, minority charge carriers. Then we will also talk about the transistor current, because these minority charge carriers, when they diffuse from P to N side, right, they diffuse the form. Similarly here. So, we will calculate these diffusion current basically, and then we will talk about the different modes of the transistor operation. For example, right now we are talking about forward and reverse. How about if we have a reverse forward? How about if both are reverse? How about both are forward? So, there are many possibilities. We are just discussing one, which is known as the active mode of operation. So, this forward and reverse is known as the active mode of operation. Okay, so let us go and talk about the things briefly. So, let me draw up NPN transistor. We have been talking about PNP. So, let us just do one NPN one. So, this is NPN. And this is forward bias because we are in the active mode. So, this is forward bias because the positive terminal of the battery is connected to the p-type semiconductor. And here this is emitter, this is base, this is collector, and here N-type is connected to the positive terminal. So, this is a reverse bias, this is forward bias, this is emitter, base, collector. Emitter current will be coming out in this case because this is NPN. If you remember, we discussed about the symbols of these transistors. So, this is collector current, this is base current. So, IE is equal to IB plus IC, that will remain valid here as well. So, first we will talk about this characteristics of IE versus this voltage which is between VBE, base and emitter, right. So, how does this vary when someone increases VB for a, let us say, constant VCB? Okay, this is VCB. So, we know that in this active configuration this is a forward biased, right. So, this will behave like a PN junction diode. So, this needs some bias voltage to get rid of this V naught contact potential, and once we are above that voltage, which is known as the knee voltage, current will grow exponentially. So, if you see VB, which is in volt, and this is the current, let us say this is in milliampere. So this will go something like this, okay, which is very common characteristic of a forward bias. Let's say VCB is constant, something here, 1 volt or something like that, and this is my knee voltage VK, which is approximately 0.7 volt. This is 0. So if I increase VCB here, if I increase VCB, let's say to 2 volt to 4 volt, 10 volt, what will happen? What will the curve look like? Okay, I'm keeping this VB constant. So what will happen? So there are two possibilities. Maybe like curve can go something like this, or it can go something like this, right? Something like this. So either this way or this way. That's the question. If VCB is increasing, answer is that curve will shift this way. Though this shift is very slight, I have a bit magnified it just to show it, but this will be a very slight and small one, but this will shift in this direction. So with increase in VCB, this will shift in this direction, and the explanation why, because see, when you are increasing VCB, what you are doing? Basically increasing the reverse bias. So this depletion region will increase, right? So more current will reach to the collector, right? So there will be less base current, IE will be more. And if we talk about output characteristics, so let me just draw the output characteristics. So as I said, there can be there can be many modes of operation of a transistor, which includes forward, reverse, which we are discussing, active mode. There can be a case where both are in the forward bias, that is saturation, and there can be a situation where both are reverse, that is cutoff, and there can be a situation where first one is reversed and the second one is forward biased. This situation is known as the inverted active mode. So we are just talking about this at this moment, and in this output characteristics we would like to see how IC and VCB vary for different IE. Okay, let's discuss first case where IE is equal to 0. Okay, and in such scenario you can say, let's say if you have a PNP transistor, so this is open circuit. Okay, this is open circuit, and some voltage is there, VCB. So what will be the current if this is open circuit? IE will not reach to the collector, there is no IE, right? So whatever current will be there because of this reverse saturation current. What happens in case of a reverse biased PN junction? So the current will be there, but that would be very small. Let's say, let's slightly shift 0 here. The current will look like something very small, right? It doesn't matter how far you go. Of course, you are not supposed to hit Jain and avalanche breakdown region. Of course, current will increase then. And if IE is having some value depending on if it is connected and the voltage, so let's say 1 milliamp, it will go this way. And then see, IC is not changing, right? For a constant IE, it is largely same. So you can say IC is equal to IE, which is what we derived basically. And in this case, because there is no IE, the only IC here is because of this reverse biased, which can be written as ICBO, where O stands for open circuit. Okay, so similarly, if you increase IE further, it will again be straight curve, whatever it is, IE 2-3 milliampere. IE 5 or whatever. So that's the basic characteristics. And if you see, if this VCB is going to be negative here, that means it is again going to be forward biased. So in this case your current will increase dramatically and you will enter into a saturation region. So this is saturation region, this is cutoff region. Okay, when both are reverse biased. So this region is basically your active region. I hope you could get some idea of these output characteristics. We will discuss them in detail now later on as well, once we will talk about the transistor operation as an amplifier. Okay, so let's discuss about the static characteristics of the bipolar transistors. So here we will have some assumptions before we go into the charge distribution, minority charge distribution in emitter, in collector and base. So let's see what are those conditions. First condition is that device has a uniform doping in each area. Okay. Also we will assume that there is no generation and recombination current in the depletion region. And whole drift current basically in the base region or in the collector saturation current is negligible. Okay, so these are the conditions, and now we will quickly look at how this profile of these minority charge carriers look like in case of a PNP transistor. So going back to the PNP transistor, this is PNP. Okay, so we know that holes will start moving from P to N side, so there will be huge IEP current. Some part of that will go towards IB. Of course, electron will move from N to P side, and current corresponding to that IEN will be in this direction, and this is the reverse biased case. So in reverse biased case, holes, minority holes will move from here to here, and electrons will move from here to here. So you can say, if you just want to show the current, IC current due to electrons, it will be in this direction, and this will form your base current basically. So if I just going to draw the distribution of, let's say, these minority charge carriers. So this is let's say this is the first depletion region, and this is x is equal to 0, and here x is equal to minus xe. Okay, and this region is another depletion region. This is wider than this one, so this corresponds to this depletion region, and this corresponds to this depletion region. So this width of the base is W here, and let's say this is XC. So this is emitter region with N positive, and this is collector region P, and this is base N. So let's say this is your equilibrium concentration of these holes in N-type region, which is Pn0, and this is equilibrium concentration of electrons in this P-type collector, which is NCO, and let's say this is the again sorry, this is P plus basically, P plus NP, and here the concentration is Ne0. This is I am talking about electrons concentration in P plus region. Equilibrium, these are the equilibrium concentrations. Now what will happen, because of this diffusion from emitter to the base, a large number of holes will move, right? And let's say the concentration at x is equal to 0, Pn0 is there, which will become 0 here. Okay, so this is Pnx, fine. And similarly here, because electrons are moving from P side to the N side, so this will be depleted in this region. They will stay here and slowly they will deplete. So NCX, this is Pnx. And similarly here, electrons will move from N to P side, right? So this will be diffusion, something like this, and this will be NEX, and this is NE0. So this is the minority charge carrier distribution profile basically. So under the active mode, because we are using forward biased and reverse biased. The first junction is forward biased and the junction is the reverse biased. So if we want to derive a mathematical expression, let's say for this particular base region, for these holes which is diffused from emitter to the hole, the equation can be written as dp double derivative of Pn double derivative of x minus Pn minus Pn0 divided by tau p equal to 0. Okay, let me explain this from where this came. So this equation is known as the field free steady state continuity equation. Field free steady state continuity equation. So this part take care of the diffusion. This is the diffusion constant, and this part take care of the recombination in this base material. So this is your lifetime of the minority charge carriers, lifetime of the minority carriers. So it's sort of an equilibrium, more are diffusing and the recombination is taking place. So let's derive more mathematics and try to solve this equation to get this profile, whether it is the linear profile or not, what we have drawn here. Okay, so let's try to derive that. First I will rewrite the equation again, derivative of with respect to dx square this is the equilibrium concentration as we discussed earlier. So a generic solution for this differential equation can be written as Pnx equal to Pn plus C1 e raised to power x Lp plus C2 e raised to power minus x Lp, which is a standard solution of such a differential equation. Okay, and Lp here, which is square root of dp tau p, basically this is a well-known diffusion length of hole. Okay, so now our job is to determine these C1 and C2 coefficients. We want to know what are their values, and we need some boundary conditions for that, right? We have framed a mathematical model or differential equation. Now we need some boundary conditions. So there are two boundary conditions. One is Pn0 x equal to 0. So the amount of dopant just at x is equal to 0 is equal to equilibrium concentration multiplied by E raised to power QVB divided by KT. Okay, this is the expression. And second thing, Pnw equal to 0 is 0. So These two are the important boundary conditions, and the reason behind is that we have assumed, because in this case here it is 0 because of this reverse biased, and we believe that because of this under reverse bias the minority carrier concentration at the edge of base collector is 0. That's why this is here at W equal to 0, this concentration profile is 0. Okay, so now implementing these two conditions into this one, and then let's see what we get the solution. So the solution comes out to be Pnx equal to Pn0 e raised to power q VEB by KT minus 1 multiply. This is a fairly complex solution. Sin H W minus X P plus Pn0 1 minus sin H X by LP sin H W by LP divided by sin H W by LP. Okay, fairly complex solution, but if you make some assumptions, just like sin H X can be written as X if X is much lower than 1. So using this approximation, and also you need to keep in mind that this approximation is valid because the width of the base here is much lower than diffusion length, and that we have to keep in mind. Otherwise, if it would be more or less same as of diffusion length, then most of these holes will be recombining in this base region, right? So we want these holes which is coming from emitter to pass through this base and to reach to the emitter. That's the thing we want. So that's why this condition is very important, and using this condition and applying it here, what we get is Pnx equal to Pn0 e raised to power q VEB by KT 1 minus X by W. So this expression is important, and this can be written as Pn0 1 minus X by W. So the important condition that you need to keep in mind, this equation is valid only when the base length is reasonably smaller than your diffusion length. Otherwise this equation will not be valid. And as you can see here, this is linear equation, right? So our initial assumption that charge carrier profile would be following this path is all good. Okay, so that's good. Now we have an equation which is representing the profile of these holes in the base region. Now similarly we need to derive the expression for others electrons in P region and emitter region and in the collector region. So if I just write down the again I draw the diagram, I can do that, let's say. So this is X is equal to minus XE, this is X equal to 0, this is W, this is X is equal to XC. So the profile here looks like this. We just discussed that. And CO, equilibrium concentration, here it is Pn0, it becomes 0 here, and this is Pn0, and here again it is Ne0, NEX, and this is Ne0. Okay, so now what these electrons in emitter case, let's say at X is equal to x minus c, just at here, at the edge of the depletion region. This is the first depletion region, this is the second depletion region, right? So that would be equal to NEO, which is the equilibrium concentration, raised by e raised to power QVEB by KT. Law of junction. These are known as the law of junction. This is what we used in the previous case here. Right. This is law of junction. Okay. So now if I talk about these electron concentration at x is equal to xc, in case of collector NC, C represents collector, at x is equal to xc, this comes out to be NC0 e raised to power minus q VCB, which is basically 0. Okay, because we know that this 0 here, all electrons will leave from here to the base region. So that's the basically boundary conditions similar to what we had. And if we write down the equation of continuity, field free steady state continuity equation for these two regions, right, for which we have got some boundary conditions, and if we implement that, we can also get the same expressions as we got for P and X, if you remember. So I'm just writing directly the expressions. If you wish, you can derive that. There is no need otherwise. So NEX equal to NEO, the equilibrium concentration, and in this we add NE0 raised to power EQVEB by KT minus 1 e raised to power x plus XELE. Here x is less than minus x. Similarly, for NCX, I am talking now about this was for this. This is NCO minus, this is important, minus sign, because concentration is going down here. On the contrary, here it is higher. So NCO e raised to power minus LX plus x minus XC divided by LC. X has to be equal and larger than XC here. So these are the expressions for electrons, electrons in p-type emitter and the collector. Now the objective of these distribution of this charge carrier was to calculate the diffusion current, right? Once we know this distribution profile, then we can calculate the current. Okay, so let's do that. So we know that the expression for current, diffusion current, from previous lectures, the expression for diffusion current is I minus QA D P, double derivative of this whole profile in this space. Right now I am going to calculate this IEP, which is due to diffusion of holes from emitter to base. Okay, while x is equal to 0. Now the expression for Pn x was, we just derived that, is this Pn0 e raised to power QVB by KT 1 minus x by W, or it is can be written as Pn0 divided by multiplied by 1 minus x by W. So we will use this expression here. So Pnx is Pn0 1 minus x by W, and derivative of this with respect to x minus Pn0 by omega, and implementing this it's same for any x. What we get is IEP minus charge will settle down QADP PNO by omega. So this is the expression for the emitter current. Of course, you can use this expression e raised to power if you want to expand in terms of Pn0. So sorry, this was x is equal to 0, and if you want to expand this in terms of Pn0, which is Pno, and expression is EQVEB by KT. So if you just want to expand this, you can write down IEP equal to QADP Pn0 e raised to power QVEB by KT divided by W. I hope you understood how we did that. Just take the derivative of this and fit into a standard diffusion current formula. Same, right now I did it at x equal to 0. Of course, continuity of the current has to be maintained. So let's do it. What will happen at x is equal to W? Okay, because you know the current derivative, derivative of this Pnx is not depending on the x, so it will remain same. So if we multiply even the current, here this current is x is equal to 0, the same expression for the current will be received is equal to x is equal to W, and that will be same QADP e raised to power Q V e raised to power QVEB by KT divided by omega. Same expression will be there, and always remember these expressions are valid. Here we have assumed W, the width of the base, is much smaller than LP, which is the diffusion length. So as long as this expression is valid, your formulas for the current are also valid. Now since we have calculated this for holes entering from emitter to the base, now we will do the same for the electrons which are entering from base to the emitter and collector. Okay, so let's do that. The expression which we got, so the expression for NEX equal to NE0 plus NEO, and then which is EQVEB by KT minus 1 e raised to power x plus XE divided by LE. X is less than and equal to minus XE, the first equation, and the second equation for electrons in hole moving from electrons in collector moving from collector to the base is given as NC0 minus NC0 e raised to power x minus XC divided by LC. X is greater than and equal to XC. So if you just do the same thing here, take a derivative, and the expression for IEN is equal to A minus QDN. Here it will be DN, in earlier case it was DP, right? Diffusion constant, and derivative of this NEX. So if you can do that, this derivative, let's say at x is equal to minus XE. So the current would come out as QADN NEO divided by LE, and this will be EQVEB by KT minus 1. So this is the expression for the current. So this is the current here because of the electrons moving from N to P side. Derivative of this basically. This will come out to be A minus QDC derivative of DNC by X with respect to x is equal to xc, and which is comes out to be QADCNC0 by LC. You can use the same expression here. So the only difference is that this exponential term is missing from here. Okay, and these are the dn and dc are your diffusion constants. So it's so easy to calculate the diffusion current once you know the gradient, rate of change, the profile of this basically charge distribution. Then you take a derivative and you multiply it with QAD, where dn or d, whatever it is the diffusion coefficient. Okay, so we have now learned some currents in the transistor. We have calculated the mathematical expression under the assumption that the width is fairly smaller than the diffusion constant. Now let's do some more mathematics to give more shape to this current so that they are easy to remember. So the IEP we calculated, I am talking about this current IEP. So I will just write down the equation here. It is QADP divided by W Pn0 and e raised to power QVEB by KT. Okay, similarly IEN QADE by omega n E0 KT minus 1. These are the two expressions we just derived. If you can see, what if you want to see that, this is the expression. Okay, so now we know that IE would be sum of these two, IEP plus IEN. So you need to add both of them. So what we get is equal to QADPPN0 by W plus QADE and E0 by W. This is Q. E raised to power VEB by KT minus QADE and E0 by W. So this is the expression we got for this IE current, and in order to make it more smoother, we can, or more representable, we can minus and add this term. So these two term and these sum of these two term is same. So we can write down IA is equal to A11 e raised to power QVEB by KT minus 1. So this term will come out. Since we have added this term, so it is QADPPN0 divided by W. This term, let's say we call it A12. This is A11, this term, and this term is A12. So this becomes I is equal to A1 e raised to power QVEB by KT minus 1 plus A12. So this way we have defined the current I is equal to A11 e raised to power QVEB by KT minus 1 and plus A12. And of course you could just simply add this expression and you will get the term. So from here, once you know the equilibrium concentration profiles, you know the diffusion constants, you know some physical parameters, W and all that, you can get these currents. So, and these applied voltages, of course. So largely the material parameters, the doping profile decides the amount of current. Okay. So of course biasing is important, forward bias, reverse bias. Now similarly we will do it for collector current, how it goes for the collector current. So collector current, you know, IC, we just calculated ICP, assuming this is equal to IEP without any loss in the base. So which is equal to QADPPN0 divided by WE raised to power VEB divided by KT. And ICN we just calculated already. ICN comes out to be AQDCNC0LC. So the only difference here compared to IEN, if you remember, that there is no exponential term, right? So that you should need to keep in mind. And in order to calculate the collector current IC, we need to add both of them, ICP plus ICN, and that comes out to be QADPPN0 divided by W e raised to power VEB by KT plus QADN NC0LC, or you can say, yeah, I'll see whatever notation you want to use. So this expression can be written also in the form of IC equal to A21, there we used 1 e raised to power QVCB VEB by KT minus 1 VEB, because this is coming from emitter to the base, plus A22. Okay. So in order to do that, what we need to do, that we need to minus some term and plus some term, right? Minus some term and plus some term. So this term we need to minus and then we need to plus it. So the expression can be written as ICQADP PN0 W e raised to power QVEB by KT minus QADP PN0 plus W plus QADN NC0 divided by LC plus this term QADPPN0 divided by W. So this term becomes your A22 and this term your becomes A21. So if I just write down them, my A21 comes out to be QADPPN0 divided by W, and A22, just this term A22 comes out to be QADPPN0 divided by W plus DCNC0 divided by LC. And this collector current can be written as IC is equal to A21 e raised to power VEKB by KT minus 1 plus A22. Okay, so this is very similar to the emitter current. This is total emitter current. Okay, so now today we have calculated these transistor currents, and first we learnt about this minority charge distribution. Once you know the distribution, you can take a derivative, multiply it with minus QAD, you will get the diffusion, right? It's very simple. And we know from here this largely depends on the doping profile, equilibrium concentrations and your diffusion coefficient. So depending on these parameters and applied voltages, you can calculate the current in the transistor, nothing else. It's fairly easy. We were talking about the current, charge distribution, we talked about I to V characteristic for both stages, forward biased and reverse biased. Now what we are going to do is, afterwards we talked about charge carrier distribution profile, and then we talked about the current in transistor. Now we'll talk about the different modes. As I've been talking since the beginning that transistors can be used in different modes. One which we have been discussing so far is the forward plus reverse. So here your PN junction is forward biased like this. This is PNP, and this guy is reverse biased. And there is a purpose for that, because as we discussed in detail in the last lecture, that this makes transistor such a way that there are two diodes sharing this N region, and this allows the transfer of the current from low resistance to the high resistance. Another possibility could be R plus F, right, where this is reverse bias and this is forward biased. So the question is that what will be the charge distribution profile in this case. So let's first discuss the case of forward and the reverse, then we'll move to the reverse and the forward. So as we have already seen that P and P case, and let's say this is our depletion region here, this is our depletion region here. So in this case it goes this way, in this course it goes this way, in this course it goes somewhat like this. So this is Pn, this is Np, this is Np. Okay, this is, let's say, 0, this is W, this is Xc, this is minus X, emitter, base, collector. Now what will happen in this configuration where we have this reverse plus forward bias combination? So far we have been discussing forward plus reverse bias combination. So it will be the other way around, like now holes are diffusing from here to here because of the forward bias. So in this case it will be the other way around. So let's say it will be something like this, it will be something like this, it will be something like this. So this is P and P, this is your emitter, this is your base, this is your collector, sorry, this is your collector. No, this is your emitter, this is your base, and this is your collector. So this has been reverse biased, that's why you see the profile like this. This junction is your forward biased, reverse biased. So it's just an inverted version of this one. So this is forward, this is reverse, it is reversed here, and this is your forward bias. So it's the other way around, and the charge distribution profile will be something like this. Now if you know the charge distribution profile, you can easily calculate the current. And if I talk about let's say other operations, so that you have reverse and reverse, so that is known as the cutoff operation, cutoff mode of operation. Here there will be no current. Okay, so charge distribution profile will be something like this. Means current will be there, reverse bias current, very very small. So it will be, let's say, emitter, base, and collector. So no movement of these huge holes from emitter to the base. Let's say this is P and P, right? And since this is also reverse biased like this one, so the profile will be something like this. Okay, no diffusion from here to here. For minority, these charge distribution profiles we are doing, charge carrier profiles we are doing for the minority charges, minority carriers basically. Okay, now we discuss last case where both are forward. This is known as the saturation region. Okay, in saturation region you have the flow from both sides. So it would be something like P and P, where both are forward biased. Okay, so electrons are moving from here to here, holes are moving from here to here, holes are moving from here to here. So if I want to draw the charge distribution profile in such a case, it will look like something like this. Something like this, depending on wherever the doping is higher, the slope will slightly move, tilt. this will be something like this as it was, this will be something like this as it was, sorry, yeah, this will be something like this as it was, to base collector. So this is something like that. So it doesn't go to the 0 because diffusion is from here to here and here to here. So these are the 4 possible modes. We will mainly use the active mode for most of the applications, especially for amplifiers. For switch, 2 modes will be used. So we'll talk about that later on when we talk about the applications of the transistors. Now we'll just summarize and we'll close this lecture. So basically we have discussed the input and output characteristics of the common base transistor. In common base we learned it follows the forward bias of the diode, and here in case of the output characteristics for a fixed current, IC is more or less same equal to your IE, irrespective of the varying voltage here, assuming this is below Zener and avalanche diode. Then we talked about the static characteristics of the BJTs, where we discussed how the charge distribution, these charge carriers are moving, especially the minority carriers, something like this, something like this, something like this, and PNP. Okay, and current, which is very very important. So once you know the charge carrier distribution profile, then from there you can calculate the current. Okay, and in the last we talked about the different modes of the operation. So there can be 4 possible modes: active, saturation, inverted, active, and cutoff. Active is the most useful, where we will be using it, will be where we will be transferring the current from low resistance to the high resistance. So to an extent we covered like how to calculate the current in the transistor, and as we have observed here, it depends a lot on the parameters like A and the concentration profiles. Basically will be concentration profiles of this doping. So doping distribution is also very important. In these calculations we have assumed these different regions basically have the uniform doping here. So but if it is varying, then things might differ, the current will be different. So there we have assumed, and the most important assumption, we have assumed that the W is much lower than your diffusion length. So that one should keep into the mind. But using these basic logics, even if you have a very exotic profile of the doping in any transistor, you can calculate that. I hope from here you will be able to learn how to calculate the currents. Then we'll talk about more in the next lecture. Thank you. Have a good day. Bye.